So we introduced last time the equations that can be used to solve engineering problems, and we said that we have several ways to solve problems. The first one is the analytical or theoretical approach, which will use laws and theories and associated equations as the continuity equation, the Newton's law applied on a certain control volume, the energy equation, to have an exact solution for for engineering problem. Now we have seen that the advantage of the analytical method is that the solution we get is exact, but the disadvantage is that in general the problems having analytical or theoretical solution are very limited. So the majority of engineering applications which involves complex physics do not have an analytical or theoretical solution. This is why we should think about other strategies to solve for our problems. These two strategies are mainly the experimental procedure approach and the numerical approach. Now, each of these represent its own advantages and disadvantages. For the experimental part, it will actually simulate the real situation, so it can take into account several effects that were neglected in the modeling or numerical approach. But in this case, the disadvantage is that we have high costs and we need a lot of time if we want to perform a complete parametric study to understand the effect of all parameters on our problem. For example, imagine that you are designing in the process of designing an airplane or a car, and each time you change a parameter, you should do an experiment. It's not very practical. This is why one of the most widely used technique is the numerical approach, which will consist on transforming differential equations from the analytical approach to numerical equations using several algorithms and schemes. In this course, we will learn the different methods that can allow us to move from analytical equations to numerical equations. And then the advantage here is that we can save time, we can save cost, but the solution obtained is approximate and not exact. Now, it's our role to try to approach as much as possible our solution to the real case. Okay, this is why in general we do like an iterative procedure between numerical approach and experimental approach. So when we develop a CFD model, we start to tune the CFD model. So we want to validate it with previous literature data or with experimental data. So what we can use then, we can simulate a certain problem. This problem we can perform experiment using same conditions, and then we compare the results. We try to develop our mesh and to develop to use different models until reaching good agreement between CFD and experimentation. Then we say that the model we achieved is predicting well realistic results, so it will work, and we can now use the CFD model to avoid getting back to experiment each time. So we can conduct parametric studies and we can make up conclusions and recommendations. So from here we define computational fluid dynamics. Computational fluid dynamics is a set of numerical methods that are applied to obtain an approximate solution of problems of fluid dynamics and heat transfer. So CFD is not considered a science by itself, but it's a way to apply methods of one discipline, which is numerical analysis, to another discipline like fluid flow, heat and mass transfer, etc. Now, what is the reason of using CFD? So we already said that computational fluid dynamics solutions are not exact. So why not to use the analytical approach? The reason is that limited problems especially in engineering field, present analytical solutions. So we need to go to other strategies or experimental or CFD. As we said, the experimental approach is a reliable technique, and we can use, for example, wind tunnel experiments to design, let's say, an airplane or an airfoil, a car, etc. But they present high cost and large time. This is why CFD is used, because we have many engineering problems that can be solved analytically, and experimental approach is difficult and will cost a lot. So concerning the difficulties, we mentioned them, the difficulties in theoretical and experimental procedures. Now, CFD presents many applications that are very interesting. It's a powerful technique that spans a wide range of industrial and non-industrial applications. In this course, we'll try to cover several applications of CFD. Some examples where we use CFD in the aerodynamics field. So when we want to design cars, when we want to design airplanes, CFD is widely used to compute drag and lift forces. It can also be used to know what type of materials should be used when designing our systems, because it can allow us to study the pressure field over the car. So we can compute the maximum pressure zones and determine what material is convenient to be used at these locations. We have also another important application in energy, which is internal combustion engines. So you can simulate the combustion process in internal combustion engines, and also you can simulate power plants and gas turbines. Another application of CFD is hydrodynamics of ships. So we can study the hydrodynamics and design correspondingly ships. Also, CFD is widely used in biomedical engineering. So we can study how blood flows through arteries and veins. Other applications include environmental engineering. So we can study the effect of ventilation configuration on indoor air quality, how particles can be dispersed in space, how we can reduce contamination between occupants in spaces. So this is a very important application, especially nowadays. So for example, let's say if you want to simulate coronavirus, how it can spread in space, you can consider that corona can be injected through exhaled particles from an occupant, and you can study how they can be dispersed in the space and how we can limit their dispersion by using appropriate HVAC configuration. One of the most important strategies to to try to oppose the spread of COVID-19, one scientist in US come up with a strategy for ventilation systems that allow to kill these bacteria and ensure a safe environment. So this field is very important and has a lot of applications. Also, for example, in a nutshell, CFD was applied in almost every disciplines and of engineering. It was used for aerospace industries and also in manufacturing of aircrafts and jet engines. And it is a very helpful tool in the design process. Here we can see several examples. So we first talked about aerodynamics, the design of cars. Each part, sometimes we just do simulation to design a certain part of the car. So let's say the spoiler, how should be the shape of the spoiler, how it can affect drag forces and lift forces. The shape, let's say, of the front, how we can change the shape in order to enhance the performance. The whole shape of the body, even the mirror, you can study the mirror shape on its own, how should it be, etc. So this is one of the applications. You can see here, for example, spoiler at the back of your car. The curves in your the curves of the body of your car will largely affect the drag and lift forces acting on your car. And there can be the shape can be optimized for better performance. Here we can see, for example, design of airplanes. So here you have a lot of things to investigate. You can investigate the pressure distribution over the airplane. Let's say here you have a zone subjected to very high pressure because of stagnation region. You have also the wings, the wings are in the shape of airfoil. So sometimes we just do study just for the airfoil part. How should it be? We can perform wind tunnel experiments to optimize this shape to favor the lift forces, let's say, which will help the airplane into lifting upward. And we try also to reduce drag forces so that air resistance will have less effect on the airplane. So here you can see, for example, the study just of an airfoil. Here you can observe, for example, the pressure field. Okay, you can see that you know from fluids that you have a flow that is uniform first, and as you approach, this line is called in fluids stagnation line. As you approach this point, you will have the formation of if you want, as you go, the velocity will decrease. If you use Bernoulli equation, your velocity will decrease and your pressure will increase. And when you reach this point, this is called stagnation point. Okay, so at the stagnation point level, you can say that the kinetic energy is completely transformed into pressure energy. And then you have maximum pressure here. Now, if you observe the velocity, you will have a velocity of 0 here and around the body, and will have flow separation. So if you can plot the velocity contours to see how you have flow separation around the airfoil. This will lead here, this separation will lead to zones here of relatively higher velocity compared to the uniform velocity here. Since the cross-sectional area is reduced and you have conservation of mass flow rate, so here the velocity will be relatively larger. This explains the lower pressure. So always they are inversely proportional if you want. For lower velocities, you have a larger pressure, and for higher velocities, lower pressure. And then here again, when you are done with this zone, you have like a recirculation zone here or wake zone at this level, and you have flow. So you have the formation of a wake region beyond your airfoil, and this wake region here is minimized because of the shape of the airfoil. But if you are treating, for example, flow over a cylinder, you will observe more. You will observe a larger wake zone. As we said, we also have heat transfer applications that can be investigated in ANSYS Fluent. Here we can see, for example, the simulation of internal combustion engines. These are the valves, admission and exhaust valves. So you can see here, you can study first the turbulence is within the chamber of combustion. If you have taken a course of internal combustion engines, you will see that it's very important to ensure a good turbulence level here in order to enhance the property of the mixture of air and combustible. So here you can study the pattern of airflow within your combustion chamber. You can study the variation of temperature during combustion, also the variation of pressure, because you will need this information to design your valves. You should know if you are exceeding the limits, the constraints of maximum temperature and pressure for the material. So for each, when we do the design phase, to know which material to use, and we should first simulate the temperatures and pressures that can be reached, and based on this we decide on the design and the material to be used in order for this application. Here we can see as performance of a pump. Also, you can study performance of pumps and performance of turbines using ANSYS Fluent. Here, for example, you can see flow over different shapes. So here, this is the case of flow over a cylinder. So you can see, for example, as we already did some interpretation for the airfoil, you have first a uniform. So here you can detect that this is a profile of velocity. How you can know this is from the grading of colors. Okay, for colors, always blue will be the lowest values, followed by green, followed by yellow, followed by orange, followed by red. So red is the most intense, and then as you go, so here you have the degradation of colors from larger to lowest. اوكي.
الكالر هي بتعني البريشر او بتعني الفيلوسيتي؟
لا، الكالر ما بتعني ولا بريشر ولا velocity. الكالر هي scale, and the graph can be a graph for velocity or can be a graph of pressure. انا كيف عرفت هون انه هيدا graph للvelocity؟ هلا اكيد انتم when you represent results you should put a scale and show, you say that I am presenting velocities and the unit, let's say, is meter per second, and you show your grade, your scale of colors. Okay, but when you will be familiar with ANSYS Fluent, you will automatically know the grade of colors. So always blue represents the smallest values, followed by so here this is, so you have grades of blue also. So for this part here it is a little bit larger, then you go to green, then you go to yellow, and you have grades of orange after. As they become more intense, you are increasing the values, and the red will be the larger values. Okay, now how did I know that this graph represents velocity? Who can tell me? Not pressure.
No, steady point.
Yeah, exactly. If you just observe the stagnation streamline, this is a stagnation streamline. Along the stagnation streamline, when you move, the velocity will be decreased. However, the pressure will be increased. So if this was a pressure graph, I should have another degradation of color. I should go from lowest to highest. Okay. So since here I have first the stagnation zone around, stagnation points around the cylinder of zero velocity, and you have the formation of a wake region behind due to flow separation. So this is the wake region we were talking about. Here you can see it in a very clear way. And this is the separation. So here you have flow separation. So as expected, in this zone, you have very high velocities because, as we said, you have conservation of mass. So due to continuity, here you have the same flow rate. So since you are restricting the cross-sectional area, the cross-sectional area is reduced compared to this one, then you expect higher velocities here in these zones. And then you will have flow separation. I will use another color to be, so let us use this.
دكتور بعد سؤال بليز.
Yes.
هلا الفرق بين السلندر والجناح اليارا.
نعم.
التربولنت فلو واللامين فلو هو اللي بيأثر انه بعدها كيف عم بتصير، انه اوكي
هلا
عم بتغير.
حتى ليك، حتى اذا نفس الرينولد نمبر، اوكي، البيهيفير شوي غير because of the geometry. يعني انت الايرفويل معمول بطريقه، اول شيء الفاريشن تبعه سموث، يعني هو بيساعدك تخفف هالويك ريجن. عرفت كيف؟ لانه بخفف الافكت اوف سيبريشن. يعني اذا بتطلع بالجراف تبع الايرفويل here، اوكي، هلا نحن هون شايفين البريشر بروفايل مش الفيلوسيتي بروفايل. اوكي، but still you can do an analysis here. اول شيء هون الويك ريجن is very limited، كثير صغيره. ليه؟ لانه تطلع بالشيب. اول شيء هالشيب اللي هو عندك سموث فاريشن من هون لهون، يعني ساعدك للترانزيشن، ما خلى السيبريشن تكون كثير قويه. بينما اذا حطيت بلوك هيك سيلندر عم تجبر السيبريشن تكون اقوى، and this will lead to a bigger zone of wake formation behind your cylinder. فانت اذا بدك الفورم of airfoil ساعدت انه ما يكون في انه تكون separation easier وما يكون عندي كتير زون فراغ إذا بدك، يعني ما يكون فيها fluid because of the smooth shape and transition that is provided by the airfoil. Okay.
هلا هي راحت انا من عندي، بس هي الايديا انه الشيب بتساعد يعني، او بتهون ليفل الهواء او
حسب الجيومتريك شيب 100%. جيومتريك شيب كتير بتأثر على الفلو بيهيفير. يعني انت تطلع وقت صار سيبريشن، بدل ما تكون الجيومتري عم بتقوي السيبريشن عم بتخففها، لانه اذا بدك الايرفويل السكشن تبعه من بعد هون عم تخف، عم تنقص، بينما عم تنقص وسموثلي يعني شوي شوي. بينما السلندر عندك sudden change، يعني عندي هون هالسيبريشن زون وكتير بسرعه عندي ترانزيشن من هيدي البارت لهونيك، فما كان عندي شيء ساعدني to have a smoother variation. اوكي. بينما الايرفويل بيعمل هيك، فبيساعد يخفف هالإفكت of separation ويخفف الويك ريجن. يعني اوريدي الويك ريجن وين كانت تصير؟ كانت تصير دغري ورا السلندر. فانت هون بهيدي الجيومتري جيت حطيت محل الويك ريجن مثل شيء سوليد، فخففت الإفكت due to separation.
Okay, thank you. Thank you.
Welcome. Other questions on this?
Yes, doctor.
Yes.
الويك ريجن بس شو بتأثر علي؟
هلا الويك ريجن يعني ما في فلو. اوكي. هلا هي اوقات it's not desired، يعني حسب الابلكيشن اكيد، عرفت؟ فهي فيها تاثر على الدراج فورسز، على الليفت فورسز. So this is how it can affect you. اوكي. يعني انت when you do your study ببين معك انه هيدا الجيومتري مثلا يمكن بتساعدني انه تكبر الليفت، وبتساعدني تخفف الدراج كمان. اوكي. لانه انت شو يلي بيخلق لك هالاوبوزيشن او دراج فورسز؟ انت اذا عندك هون ديفرنس كثيره بالفيلوسيتي بين هالريجن وهالريجن، this will create a large pressure variation. عرفتي كيف؟ بين هون وهون. هذا الشيء يمكن ما يكون desired. You don't want to create this high difference of pressure between your front and your back. Okay. So depending on the application هالويك region معقول تكون عندها disadvantage أو لا، يعني يمكن ب other situation تكون desired. So it depends on your final goal of design.
Okay, deal. Thank you.
Okay, welcome.
دكتور.
Yes.
هلا نحن بالايرفويل بهمنا يكون عندنا ليفت، الفورس تكون قوية لحتى يقدر يشقل الايرفويل، صح؟
صح 100% مظبوط.
الليفت فورس هي مش ناخدها مع البريشر؟
الليفت فورس لها علاقة إذا بدك مظبوط. هي النت فورس. أنت منشان هيك الايرفويل ما بيكون سيمتريكال. إذا بتستعمل سيمتريكال ايرفويل حتطلع النت فورس عندك زيرو نت ليفت، فأنت بتلعب بالشيب بطريقة إنه الأوفرول ليفت تكون لفوق. يعني هي كيف how we compute هالليفت فورس؟ we calculate pressure forces على الupper part والbottom part. اوكي. وبنعمل البالانس. فانت يلي بدك اياه انه يكون الفورسز على اللور بارت هاير، يعني بدك تعمل الشيب بطريقه انه تكون التوتال ليفت لفوق. وهيدا الشيء فيك تقشعه بهيدي الفيجر. هيدي الفيجر represents the variation of pressure. You can see that pressures at this level are larger than pressure here, which is good. Okay, because this will lead to an overall balance that is upward. بينما لو كان الشيب سيمتريكال، يعني بتلاحظ انه البروفايل على الابر بارت غير البروفايل على اللور بارت. اوكي. فانت they studied how to optimize this profile to create this effect. يعني شو هو البروفايل of airfoil يلي حيخلي عندي overall balance للpressure forces that is up, which will lead to a total net lift that is upward. اوكي. بينما اذا بتستعمل completely symmetrical shape like this المفروض يكون في symmetry بالفيجر تبعك if you neglect اكيد الويت effect.
اوكي بس في شغله انه هي البريشر مش كل ما كان في كونتاكت كل ما اكتر. فهون بالاير فويل مبينه انه من تحت سموث اكتر، يعني
مش
كيف عم
قصة،
يطلع
لا
عندك؟
لا مش قصة كونتاكت بس ليك. ما هي الفكرة انه البروفايل اوكي حيأثر على الاير فلو ديستريبيوشن. اوكي يعني لاحظ هون مثلا عندك هيدي الزون كسكنس اصغر من السكنس تحت، صح؟ وانت كل ما نقصت السكنس، يعني كل ما كان كل ما السكنس اقل كل ما الفيلوسيتي فوق حتكون اكبر. يعني reducing the thickness here comparing these two الفيلوسيتي هون حتكون اكبر، فالبريشر higher، فالبريشر حتكون lower. فانت فيك تعمل ديزاين بطريقه انه اذا بدك اذا بتي compare to the center line اوكي بيكون عندك هيدي البارت اقصر من هيدي which will create اذا بدك هون بهيدي الزون velocity that are larger و pressure that are lower، وهون من تحت بالعكس. So this will create a delta P in this direction and this is what you want to do. هيدي هي الفكرة. يعني
غير احنا بدنا الفكره ناخذ
نعم
انه نجيب ليفت من
sorry it's lagging a little bit. Can you repeat, or if you want you can type it in the chats. Any other question before we continue? Let me check chat. Look, إذا أنت الapplication للairfoil هي airfoil for a is used to design the wing of an airplane, yes, the goal will be to have a net positive lift force, of course. لأنه lift بيساعدك تقليعة الطيارة وتطلع طلوع. Okay, so here this airfoil is used for the design of a wing of an airplane, so it's desired to have a lift force that is up. يمكن for other applications يكون different purpose, so always you should set your objective and based on this you decide on the geometry. من هيك عندنا عدة geometries للاirfoil حسب وين بدنا نستعملهم. في applications يمكن ما بيهمك الليفت، فيك تعملها symmetrical. ساعتها بتشتغل على drag effect. So it depends what you want, what is your purpose from using this geometry, you decide how should it be. Okay. So here for example, so here you can see the profile of velocity from, if you want hey this section, let's say showing a cross section بالwind tunnel. Okay, so here you have two views from top view. Okay, and also here you can have a profile view of the distribution of flow in your يعني هيدي غير هيدي you can have different presentations. يعني هون مثلا in this figure you could have taken إذا بدكم إذا هيدا الwind tunnel. Sometimes we change the view in order to get additional information. So if this is the wind tunnel, for example, and this is your cylinder here. The cylinder can be placed in different ways, okay? It can be placed like this in the vertical position. كمان it can be placed in the horizontal position, and each case will give you a different profile. Okay, here for example, if we consider this figure, okay, as the first one, ساعتها بنكون عم ناخد view from like this، نعمل cut like this and we are looking from top. Okay, another possibility إذا نحن عم ناخد cylinder like this, we can take a cross section, another cross section to observe the flow behavior. Okay, so for each scenario you can take several cross sections and observe what is happening. Now, this figure here is another application here. This figure, حدا في يقول لي شو معقول تكون؟ This one. What do you think? This can be the presentation of what?
يعني إذا السلندر هلا محل الراد along يعني بيطول الراد كله المفروض تكون الفيلوسيتي سوري البريشر.
اوكي اول شيء هون ما في سلندر، تقلكم ليه؟ انتم بس يكون في سلندر مفروض يبين، ما بيبين الوان، ببين جراي. يعني when you do a cut وفي solid ببين جراي. يعني بهالفيجر بين عندي انه في solid هون، يعني هيدي الكيس of a vertical cylinder وعندي flow over the vertical cylinder وانا عم طلع from top. اوكي now if I consider this figure here ما في عندي ولا ما في عندي gray color، يعني ما في solid جوا. اوكي
يعني هذا تيوب
هيدا tube. Yes, very good, very good. هيدا velocity profile in a duct or tube. Okay, so here I can have a duct of circular cross section مثلا, and I'm investigating the profile of velocity through this duct. Into from your study in fluids, if you remember, you considered the let's say the case of laminar flow in a circular duct system. بين معكم انه the profile is parabolic. So you can verify this here. From the non-slip condition at the walls you have zero velocity, and the maximum is at the center line. So as you approach the center line, the velocity is increasing. So this can simulate the flow in a pipe. Okay, the flow profile in a piping system.
دكتور يعني هيدا داكت وانا قصه vertically ما هيك؟
مظبوط 100%. هيدي vertical section of a duct exactly. حتى كمان اذا قصيته horizontally حتقشع نفس الشيء اذا circular duct. اوكي
اوكي.
This is a simulation of what in this figure?
Heat exchanger.
Yes, very good. It's a heat exchanger. Okay, so here you can see عندنا cross flow heat exchanger. فعندنا two flows perpendicular. Okay, so here for example depending on the direction, let's say the fluid in these tubes are directed like this, so you are cooling fluid. If you are passing the fluid in this direction it's being cooled لأنه بيبين عندنا هون مثلا الred color ورجعنا صرنا blue. Okay, so this is a possible scenario of cooling a fluid in a heat exchanger. أو إذا بالعكس أنا عم مرق الفلويد like this, so I'm heating it. So it depends on I need to know how the direction of the flow to determine what is happening. Okay, so this is a heat transfer application. Now you can compare using CFD different configurations of heat exchangers. So you can just change the geometry according to the type of heat exchanger you want to investigate, and then you can put your inputs and see how the temperature is varying to determine the performance of your heat exchanger. So we have covered different, we have considered different engineering applications where CFD is used. Hopefully in this course, we will try to go over many of these applications, and you can select as project one of these applications or any other project that is interesting for you. Now, in order to solve such problems, okay, when we talk about numerical techniques, or we can do our own coding, and we can write a MATLAB code to solve a certain simplified problem, or we'll do this together in the course material. Okay, we'll see how to solve, for example, conduction convection problems. We can write a programming MATLAB code to solve it. We can also use a software. So more the problem is complex, using the software will facilitate things, because in the commercial software already you have several programs implemented, and that can solve a large a variety of problems, engineering problems. So CFD will consist in solving basic equations of fluid flow and heat transfer by application of numerical techniques. And we have different approach, as we already said, or we use, let's say, developed commercial codes, or we type or we write our own codes. So you can use softwares as C++, you can use MATLAB to write your own program in case you have a certain problems that is not very complex. But whenever you get complex geometry, like the case of a car or airplane, it's really heavy يعني, to write your own code. ساعتها بتكونوا you are developing again what was done before. يعني مثل ANSYS Fluent took a lot of time to be developed, and a lot of skills and algorithms were implemented in it. So of course, whenever you have a complex problem, it's better to go to a commercial CFD code. Now, what is nice about the CFD code is that it's always under development, and you can contribute to its development by implementing, let's say, your own coding to it. So in case, for example, you have an aspect you want to model that is not present already in CFD Fluent, you can write a C code and you can connect it to CFD, so to Fluent. So this is one example where you can advance, if you want, using your programming, you can advance features developed by a commercial CFD code. Now, in general, we have a lot of CFD software packages already developed, including ANSYS Fluent, StarCD, OpenFOAM, COMSOL. And in this course, we will try to learn how to use ANSYS Fluent. Now, in any, you will see that if you go over several commercial CFD packages, they all will be similar. So you will always have some common aspects in these packages. First, any of these packages will include mainly three elements, which are a preprocessor, a solver, and a post-processor. What do you mean by this? So in any, if you have an engineering problem to solve, the first step will be to draw your geometry and to mesh it, which means to decompose it into small control volumes. So this is the role of the preprocessor. So once you define your problem, you can decide on, and you do some simplifications. And for example, if you are studying an office, a heat ventilation system, maybe let's say the presence of a chair will not affect a lot the flow behavior, you can say I will remove it. Or if you don't have a large gradient in temperature, you say I will not consider radiation. So you decide on all, you put a lot of assumptions, simplifying assumptions that can facilitate your the solution of your problem. So first, once you decide on the elements that will really affect your ventilation system behavior, you can draw user geometry and then mesh it. After this, in the solver part, you will numerically solve for the fluid flow equations in the computational domain. And here you will select the appropriate algorithms and physics to include within the solution. After this, the last step is the post-processor. In this step, then you will observe the result of simulation, you will analyze them, and you will represent them in useful form. So in any of the CFD packages we talked about, COMSOL, ANSYS Fluent, CFX, etc., you will have these common aspects. Now, we will see these three main elements in ANSYS Fluent.